Today, we're going to be reviewing Module 6 of HSC, which is all on sort of, well, electromagnetism and how they sort of relate to motors and generators and things that we kind of use every day. So there are a few key concepts that are all interrelated. So I'm going to assume you know your things from Module 4, so about electric fields and so forth. And now we're going to start getting into, well, the motor effect. All right. So the motor effect is basically when a moving charge is passed through a magnetic field, which is represented by a B, then it experiences a force. Now, force is a vector, so the magnitude of this force is calculated by Q VB sine theta, where Q is the charge of the particle in coulombs, V is the velocity in meters per second, B is the magnetic flux density, which you can think of as the magnetic field strength. In Tesla. And theta, importantly, is the angle between the velocity of the particle and the magnetic field. So in other words, if I have a magnetic field going like this, now remember crosses mean into the page, and dots mean out of the page. So this means that your magnetic field lines are going into the page. And remember, when you're dealing with things in electromagnetism, you always need to think in 3D because there's three sort of axes that you're talking about. So we're going to have a positive particle heading to the right, for example. And so if this positive charge has some charge Q and is approaching this magnetic field with strength B at velocity V, then it will experience a force which is equal to QVB sine theta. Now, remember, it's 3D. To determine theta, you need to determine the angle between the velocity, which is going to the right, and B, which is going into the page. So I highly recommend, if you're having trouble with things like this, then you get out a few pens. So you get one pen and you point it in the direction of the part of velocity. So in other words, you just lay your pen flat on the paper, right? And then you've got another pen being in the direction of the magnetic field. We understand it's going into the page, so you've got a pen just sticking into the page, right? So if you have that out in front of you, it's probably quite clear to you, hopefully, that if you've got a pen sticking into the page, and then you've got a velocity going to the right, then firstly, theta is 90 degrees, okay? So then, in this scenario, theta is 90 degrees. And in fact, it doesn't matter on this plane which way this, I could write that's 40 degrees, or I could do, say, 70 degrees. In all of these scenarios, because my pen is flat on the page and the other pen is sort of sticking into the page, it's going to be 90 degrees regardless. So just be careful of that, all right? That's something that many students get tripped up with. They aren't able to, they determine the angle incorrectly, especially when we've got a particle going sort of in a diagonal direction. Okay, so reiterating, if you have your force is going to be QVB sine theta, that's the magnitude. But of course, the force is a vector, so you also need a direction. Now, the direction in the case of the motor effect is going to be using the right-hand palm rule, otherwise known as the right-hand push rule. Now, in terms of right-hand palm rule and right-hand push rule, you can basically think of this as, I guess, the high five rule, because like a lot of people get confused between what's the right hand palm rule and the right hand grip rule, which you also need to know, of course, from year 11. So in a way, the technical terms, or the terms everyone calls them, is the right hand grip rule and the right hand palm rule / push rule. But you can think of it as a high five and a sort of thumbs up, right? So those are your two different sort of positions. Now do pay attention to the fact it's the right hand. You do have to use the right hand, because if you use the wrong hand, you get the wrong answer. But basically, in our scenario there, you just remember that with your thumb on your right hand, it is the direction of the positive charge. So that means the velocity of the positive charge. Your fingers are going to basically be the direction of the magnetic field. So in this case, pushing into the page. And your palm is then going to be giving the push. So it's a force. Think of it as your push from the palm. So in this one, you'd be having your fingers directly into the page. With our positive charge going to the right, your thumb will be pointing to the right, and that gives your hand a sort of upward push. So that means your force here would go to the right. As we briefly revised yesterday, it would be helpful to recognize as well that if you've got a positive charge entering a magnetic field, it will undergo circular motion. And you can show, and have been asked in fact to prove before, that the radius will be mv over qb. But that's just basically relating your advanced mechanics from yesterday by equating fb equals fc. All right, so I'll leave that for an exercise for you to do, but we've done that previously. All right, now the motor effect is often, I mean, it's really the same thing, but the motor effect is also applied to current carrying wires. So you may see it referring to a current carrying wire in a magnetic field experiences a force. Now the magnitude of this force, very similarly, if there's a magnitude and a direction. Now the magnitude of this force is calculated by F equals BIL sine theta, where F is the force in newtons, B is the, I'll just call it magnetic field strength here, in Tesla, I is the current in amperes, L is the length of the string in meters, and theta is between the current direction and the magnetic field. There's the angle between the current direction and the magnetic field. Now, keep in mind, of course, you should know from module 4 that current is really just a flow of charge. So actually, F equals BIL sine theta can be derived from F equals QVB sine theta, or vice versa. So it's really the same thing, just in different contexts. We're just subbing in different things to really represent the same thing for units that are convenient, right? If you have a wire, it's convenient to measure current in amperes. You're not trying to measure each individual charge in coulombs. If you have just a charge, then you could convert that into an equivalent current, I suppose. But it's usually just much easier to think about it in terms of the charge and velocity, because you should know from year 11 that current is, well, Q over T. So there is a direct conversion there. Because it's really the same thing, the direction is exactly the same. It's still a right-hand push rule. There's no difference. Right? So your thumb is still the direction of the positive charge, which you can think of as the current, because current is the flow of positive charge in terms of conventional current I. And then, of course, everything else is the same. Fingers is the magnetic field, and your palm is giving you your force as a push. Now, we've stressed this, but do remember you have to use your right hand, and your thumb is always the direction of the positive charge. If you have a negative charge, it's very simple. Just flip it around, right? I flip one of these things around. Either do it as a positive charge and then change your answer at the end, or change the, if your negative is going to the right, think of it as the positive going to the left. Flip the direction. Or you can think of it as, I'll use my left hand, because the left hand will give you the wrong answer for the positive charge. So Whichever way, just do one of, like basically just take the opposite for one thing, and then you'll be fine for negative charges. So that is the motor effect, all right? You've got, if you have a moving charge in a magnetic field, you're going to get a force, F equals QVB sine theta. The direction is given by the right-hand palm rule. Equivalently, you also have it on wires, and that's F equals BIL sine theta. Now, you should know from year 11, of course, that every wire, right, from Orsted's law and so forth, that basically a current carrying wire creates a magnetic field. So if you have a wire and it carries a current, then it creates a magnetic field. So this is more year 11 work, but it's good to sort of review this here. So remember, any wire that carries current will create a magnetic field, and this magnetic field can be calculated as basically a constant times I over D. That constant on your data sheet is going to be written like so, and it's the K is approximate, well, actually defined to be 2.0 times 10 to the negative 7 times the current over D. So it probably makes sense that the higher the current, the stronger the field, and D is just how far you're away from the wire. The direction of the magnetic field is, use your right hand grip rule, number 1, to determine the direction of the magnetic field. And basically, it's like a thumbs up situation. So I would highly recommend that you wrap your fingers around a sort of pen, which would represent the wire. All right. Every time you've got using the sort of right hand grip rule, and you have your thumb, your hand in your sort of thumbs up sort of position, your fingers are wrapping around something. In the case of application to a wire creating a magnetic field, they're wrapping around the wire to demonstrate that it's wrapping around the wire. And so keep that in mind. Lots of students are not very clear on the fact that it's a circular sort of direction. It makes no sense to talk in the general about the direction as left, right, up, or down. If you talk about the entire field, you'd have to talk about it in terms of clockwise or anti-clockwise. So this is clockwise anti-clockwise when viewed from the top. But be careful as well when you're talking about clockwise or anti-clockwise, because it's anti-clockwise when viewed from the top. Okay, but if you're viewing the same thing from the bottom, this observer from the bottom looking this way would see that as clockwise. So just to be doubly sure, I would recommend, I mean, in multiple choice, you just kind of go by the perspective they give you. But if it's like extended response, or if you're not clear, I would specify which way you're looking at it. So in this case, anti-clockwise when viewed from the top, or clockwise when viewed from the bottom. All right. So as a tip, always wrap your fingers around, like e.g. a pen. All right. And then your fingers, in this case, from rule number 1, would represent the magnetic field direction. And your wire, so your thumb, would represent the current direction. Conventional current, to be clear. And to be clear, your pen that's being wrapped around would represent your wire. Now, some students get confused why I call this right-hand grip rule number 1, because you also actually have a right-hand grip rule number 2. It's, we still call it right-hand grip rule, but actually, you might remember from your year 11 work, you have solenoids as well, which have a north and south pole. And when you're trying to determine the north and south pole of a solenoid, you will use this again in year 12 as well. So let's say you've got a solenoid wrapped like so. From year 11, you understand this is the positive terminal and this is the negative terminal, which means your current is flowing this way. And so now you have a solenoid, and you understand from your solenoid that it will create a magnetic field, basically because of the fact that current creates a magnetic field, and this solenoid will mimic a permanent magnet. And so there's a north pole and a south pole. And you've been taught to use the right-hand grip rule to determine the polarity of a solenoid. Now, they both call the right-hand grip rule, but they actually have different applications. Remember, the application we said earlier here is figuring out the magnetic field lines with relation to current. Okay. While they are related to each other, if you're trying to directly work out the magnetic field without thinking about how the wire wraps and blah, 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 then you basically will probably be better off thinking of it as a separate rule that happens to use the same hand position. So again, I would wrap, because it's a right-hand grip rule, wrap your fingers around a pen. And so the pen here would represent sort of the cylinder in the middle that the wires wrap around. And so your fingers are representing the current direction. So in this case, you'd be getting your fingers kind of wrapping sort of forward like so. And then, of course, your thumb would therefore be pointing that way, while your sort of pen is here gripped in your fingers. And your fingers are wrapping out like that because that's what mimics this sort of current flow, that they're sort of in front. On this side, in front of the cylinder, they're going down, and behind the cylinder, they're going up, which is exactly what happens with the wire. And so that means you're going to get the thumb pointing that way, which indicates that this is going to be the North Pole, and this will then be the South Pole. Okay. So hopefully that clarifies things. The reason why I talk about it in right-hand grip rule number 1 and right-hand grip rule number 2 is just to make sure that you're clear that there are two separate applications for a right-hand grip rule, either for determining the polarity of a solenoid, like we're doing here. We're calling that right-hand grip rule number 2, where your fingers represent the current direction and your thumb represents the North Pole. Clearly, the other is the South Pole. Alternatively, the other application is not to determine North or South Pole, but to determine which of the magnetic field lines go when you've got a wire carrying conducting current. Okay. Now, with that in mind, because of the fact that wires create magnetic fields, then just very briefly recall that if you have wires carrying current near each other, I1 and I2, then they will exert forces on each other. So if you have I1, it will create a magnetic field, which I2 is in. And I1 and I2 will both create magnetic fields. If you're asked to explain why this happens, you'll have to say that the current I1 creates a magnetic field, according to Orsted's law. The current I2 also creates a magnetic field around the wire. Both of those magnetic fields then interact, which then causes a force to be experienced. Now, this force is going to be towards each other when they're going in the same direction, and they'll be repelling each other when they're in the opposite direction. So the force per unit length is given by K, I1, I2 over D, which of course is this K. Okay, and then the directions, if it's the same current direction, then it's attraction. If it's the opposite current direction, then it's repulsion. And we'll be looking at some of that in the later questions as well. Okay. So that's basically all your motor effect. Now we'll need to basically move on to electromagnetic induction. And really the key part of electromagnetic induction is understanding all your different laws and how they fit together. It's kind of like a loop, all right? So we're going to start with a particular action, although it might not start particularly here, right? But the fact is electromagnetism is talking about how electricity and magnetism are interrelated, and we're now kind of drawing it in together. So you could have what's called a change in flux. So I suppose before we do that, well, let's just quickly review what flux is. So we have the concept of magnetic flux, which is given the sigma phi, and this is measured in the unit of Weber, WB. And basically, you can think of this as basically the number of magnetic field lines, basically. So the more magnetic field lines, the more Weber, the more magnetic flux, right? The magnetic field line is representing magnetic flux. Now, often we're concerned with magnetic field strength or magnetic flux density. Okay. So in terms of magnetic flux density, then that is basically, well, think about it, right? If you've got flux in a certain thing, right? You've got flux. It's like population, right? You've got a certain number of people, but if you want to know population density, then you have to divide by area. So B, which is formally magnetic flux density, is phi of A. Okay? A is area in square meters, being the SI unit, and B is magnetic flux density. In terms of Tesla. So to be clear, 1 Tesla is, well, 1 Weber per square meter. Right? Because basically the Tesla is a unit of magnetic flux density, and that's basically then representing 1 Weber for every square meter. Now for HSC purposes, magnetic flux density is assumed to represent the same thing as magnetic field strength. So for your purposes, they're exactly the same thing. So don't worry about any distinctions, probably beyond our course if we're going to worry about it. But just take B, magnetic flux density, as magnetic field strength. If you see magnetic field strength, it's B. If you see magnetic flux density, it's B, as far as you're concerned. End of story. So that's basically flux. And so you may need to use B and A to calculate flux at times, but basically that's what magnetic flux is. It represents the magnetic field lines. You understand we say magnetic field is stronger if the magnetic field lines are closer, which is represented by a higher magnetic flux density. And there you go. So we're going to look at how electromagnetic induction occurs. And through your experiments, Faraday's experiments, basically, we firstly start with a particular point where, let's say, we have a change in magnetic flux. Okay, right? So if there is a change in magnetic flux, and for all your questions about coils, just quick side note, you're always considering the inside of the coil. Don't worry about the outside. So if you have a change in the magnetic flux, then we actually will notice that there will be an induced EMF. Now, as long as there is a change in flux, then according to Faraday's law, and that's the link here, Faraday's law tells us that the induced EMF will be related to the rate of change of flux. So as long as there is change in flux, which obviously will take some amount of time, but as long as there is any change in flux, then you'll get your induced EMF. Now, you may or may not see this formula with a negative in front and an N in front. I can add those in, but the key concepts you should take from this at the moment is that as long as your coil experiences a change in flux over some period of time, if it experiences a change in flux, then there is an induced EMF. But the size, the magnitude of that induced EMF is directly related to the rate of change of flux. Okay. Now, some students are perhaps not clear about how flux can change, but flux can change in all sorts of ways, to be clear. So the key concept is if flux changes in your coil, then you'll get an induced EMF. But there is many ways we could change the flux, all right? So we could change the flux by, for example, making the magnet stronger. We could change the flux by making the current stronger. We can change the flux by changing the area of the coil, because remember, flux equals B times A, right? We can change the area. We could change the B, right, to change flux. We could also change, now, so that's how you change flux. But EMF is the rate of change of flux, which means anything that affects the time as well, even if you don't change the flux at all, even if you don't change the change in flux, even if you don't change delta phi, but just change how quickly that happens, that will also affect EMF, because EMF is not the change in flux itself, it's the rate of change of flux. And that's very important to understand. For some of you who may be more mathematically inclined, you may prefer to think of this as the derivative of phi with respect to t, if you prefer. But if you like, for your course, you don't need to think about it in terms of calculus. You can just think about it in terms of a discrete unit in time. Okay, but anything that changes the time unit will also affect, it might not affect the numerator here, but it will also affect your overall fraction, which is your induced EMF. So if things are moving faster or slower, or if they happen basically faster, then it will affect that. Okay. We'll explain the negative and we'll focus on the N a bit later. But the key point is, again, induced EMF is related to the rate of change of flux. And now that you've got an induced EMF, which essentially for your purposes is voltage, that voltage will then induce a current. Which ultimately is basically an I, right? And you kind of know this, right? Essentially, you're going to get voltage. I mean, basically, you agree that if you have a closed circuit, then the voltage will then cause a current to flow, okay? Now, you also know from what we reviewed earlier, and we need a bit more space, so let's get rid of this. Let's move this up a bit. There we go. All right, so with an induced current, with what we've already sort of established, an induced current will actually, I mean, it's current after all, it's going to create a magnetic field. And we know that because we just went through it. According to Auster's law, your magnetic field created will be Ki over d. So as long as you've got a current, it's going to create a magnetic field. And that magnetic field, I mean, by definition, is going to generate magnetic flux. So this will then basically loop back to the start. And so the electromagnetic induction is kind of a sort of loop. I think things will continually happen essentially. If you have a change in flux, by Faraday's law, you're going to induce an EMF. And that EMF will then create a current, assuming you've got a closed circuit. If you don't, then it won't. You'll just create the EMF, which is very possible, right? You can have voltage without current. But once you've got your current, it's going to create a magnetic field. And that magnetic field is going to create a flux. And so it's going to further affect the change in flux. Now, imagine if the magnetic field then further reinforced the change in flux, then that means that you're going to then further get this numerator went up. So you're going to get a bigger EMF, a bigger current, and then more stronger magnetic field, which then goes around again. And so you'll get a continual loop, which will be like a positive feedback loop. And if you keep going around an infinite number of times, you're basically going to get an infinite voltage and infinite current. That probably makes no sense, right? Like you can't just get any small, tiny, minuscule change in flux, which will then loop around to give you infinite voltage and infinite current, which means you have infinite power. I mean, if you did, things would blow up all over the place, and also you wouldn't have any questions about, energy sort of. You'd have an issue of too much energy, not an energy problem. So that's obviously not what happens, which suggests and leads to Lenz's law, which says that the direction of the induced current and induced EMF must be in such a direction that the magnetic field will oppose the original change in flux. So basically, think of this as an electromagnetic induction friction, right? You want to go to the right, it's going to push back against you. You will push left. You want to go to the left, it will push back against you. You want to go up, it wants to go down. You want to go down, it wants to go up. So it's kind of like the friction inside an electromagnetic induction system. Lenz's law, there's always some sort of pushback, all right? So that's basically induction, and then it's going to be applied very broadly, okay? So your induced EMF can be applied to any sort of induced EMF. And so specific examples of that might be sort of back EMF, okay? Your induced current is going to be applied to sort of all currents that are induced. So specific examples of that might be applied to, for example, your eddy currents. But in general, any induced voltage, including, generators, are also induced EMF, really, right? And your power plant generated currents are induced currents, right? We don't call them eddy currents in those situations because they're flowing in wires where we're designing current to flow, but where eddy currents generally are when they flow in conductors and not wires. But all of these concepts then basically tie together to give you all the different things you might be considering, like electromagnetic braking, metal detectors, or induction cooking, or anything like that. So just to be clear, let's just point this out now. This negative here is basically Lenz's law. So in your sort of formula sheet, you'll see it with Faraday's law coded with a negative. That negative is only indicating direction, which is really basically comes from Lenz's law. And if you see it with an N, it's just representing the number of coils. So if you think of phi as the change in flux in one coil, then sure. And you have more than one coil, then you multiply by N, right? To get the total number of coils. But basically, it's the total change in flux across all your coils in terms of the rate. So if you are thinking phi in terms of only one coil only, then yeah, you need to multiply by N for the total number of coils. If you're thinking of phi in terms of the total flux going through the entire sort of solenoid, well then you've already, that N would be inside the phi kind of thing. So that's basically the idea. Okay. So we'll briefly then cover motors, and then we'll basically then get a start on the questions. So in terms of motors, the way motors work is they use the motor effect. So you're going to have for example, North Pole and South Pole, and inside you're going to have a coil. Now, simplistically, the key thing you need to understand with motors, with any motor, is that you need a magnetic field. And you can get that in all sorts of ways. I've represented that here in terms of permanent magnets, but you need a magnetic field and you need a current in a wire. So all your different motors that you have, no matter how they get the magnetic field or how they get their current, they will have some magnetic field with some current. Now, basically, you use the motor effect. So if I draw this out in a 2D manner, then I have the current going like this. So if I have AB on the left and CD on the right, so that means AB is going to go into the page here, and CD will come out of the page. Using your right-hand push rule, I mean, you understand that your magnetic field strength is magnetic field lines are going to the right. Use your right-hand push rule, you'll recognize that this will go down. You've got a force pushing down, and that will be pushing up. So because your motor will be fixed in the middle, that will then cause this to turn. Okay. So simplistically, by applying a current through the coil in a magnetic field, then this will cause this to turn. Now, if it turns, you'll reach a situation where this is still pulling down, this is still pushing up. So that means while it is still going to start turn, it's going to decrease. So key things you should probably understand that in the simple examples of the motors we're talking about here, the direction of the force is, well, constant in the sense that it's always up, down, right? We might flip it with a commutator, which we'll get to in a moment. Certainly the magnitude of the force is constant. The direction of the force is constant in the sense that it doesn't turn with the plane, but it may flip. So is going to be perpendicular to the magnetic field in that sense. But it could be upwards or downwards. The magnitude of the force is constant, but the torque varies. Because torque is the sort of turning power, then it depends on basically the angle. So for torque equals force times sort of the distance to the pivot. So just keep in mind for a motor, and you often get tested on this in multiple choice, which we'll look at very shortly, your force magnitude is constant. The force direction is perpendicular to the magnetic field and switches either through a commutator or otherwise every half turn. And the purpose of that switching is to maintain torque in the same direction. But although torque is maintained in the same direction, torque generally varies as the plane rotates. And you can calculate it. I'll deliberately use a different angle here. So in your formula sheet now, I think they use n equals BIA sine alpha, like sine some angle. Just note that if you're using sine, then this is the angle between the normal to the plane of the coil and the magnetic field. So in other words, if you've got the North Pole here and the South Pole here, and your magnetic field lines are going like so. In the very start, you've got the normal to the plane like so. Normal, so it's 90 degrees. Since the normal to the plane is also perpendicular to the magnetic field, then this will be alpha in this scenario. Of course, on the other hand, if I had it on a slant, if it had already started turning, then using sine, you would then firstly need to find the normal. And then that means this angle here will be alpha. Okay. Just to be very clear about what angle that's talking about. Okay. Keep in mind your motors include DC and AC. So the key difference between DC and AC motors, apart from, of course, the current that they accept, is their design. So there are various designs of both. The key aspect that you need to be aware of is the fact that if it's DC, then you're going to have a commutator that is going to be split ring, and for AC it's going to be slip ring. Now both DC and AC motors will, that's the primary difference, but in terms of the electricity accept, it's quite obvious it's DC and AC, but they will also both use brushes. Now, in terms of the purpose of the commutator, remember the commutator's purpose for all motors is to allow the coil to rotate without the need, without getting the wires entangled. And then for DC only, to DC only, it is to also mechanically change the current direction. Every half turn. Quickly reviewing transformers. Transformers, you understand, typically think of it as a device that you use to change the voltage. So a transformer's device used to change the voltage. The reasons we do that are numerous, but for that reason, a step-up transformer, two-type step-up, is going to be when your primary coil has a lower voltage than your secondary coil. So this is your input, and this is your output. So basically, you'll have a step-up transformer where the input voltage is lower, the output is higher. Your step down is the reverse, of course. So your input voltage is higher, and your output voltage is lower. Now, as a result of that, you actually have that's a result of using electromagnetic induction with your number of coils. And because power needs to stay constant, it will actually also affect your current as well. And it achieves this by using the number of coils. So you can think of it as the primary coil will have more turns. The secondary coil will have less turns. Of course, for a step-down transformer, it's the other way around. So you're going to have less turns. My mistake there. For a step up, you want to have less turns in the primary coil, and the secondary will have more turns. Conversely, a step-down transformer will have more turns in the primary coil and less turns in the secondary coil. And that affects your sort of current on the primary side, and your current on the secondary side. So because you stepped up the voltage, that means the current went down. Okay, so this will be a higher current and a lower current, and this will be a lower current, and to give you a higher current. Perhaps more simply, step up a volt transformer, voltage goes up, current goes down, more turns on secondary. Step down, voltage goes down, current goes up, more turns on primary. And not only do we know as more turns, you basically have a formula for it. Okay, it's proportional to your voltage. So basically, the voltage in your primary over the voltage out in your secondary is directly proportional to the number of coils on the primary over the number of coils on the secondary. And the reason that's the case is basically because of Faraday's law. Okay. You can, of course, then also have this relationship of that's equal to I out over I in. But I personally would prefer that you think of it as, because especially the step up and step down sort of terminology, think of it in terms of voltage, think what happens to the voltage, then consider that power must be constant, P equals VI, and then think what happens to current. Okay. Now, the reason why transformers work, of course, is because you've got this iron core, which then creates the flux to go across. So the change in flux here is equivalent to the change in flux there, and then you've got the number of coils to sort of balance that out. And so you might just also need to remember that there will be the transformer inefficiencies are going to result predominantly in your course from eddy currents. There are multiple other losses, in fact. And so to try to basically reduce power loss in transformers, we laminate the iron core to reduce eddy currents. So you can actually laminate the iron core, or you can also simply replace the iron core with ferrites. The point of that is it allows flux to flow, but not current. So that's a reasonable solution as well, because the eddy currents require a conductor. And the reason why we need something there in the first place is because we want the flux to get from the primary coil to the secondary coil. If you can let the flux flow, but block the current flowing, well, that would be great. And we use, one just point that you should know is that we use transformers in a power grid. to reduce energy losses in transmission. So typically that's when we do a long distance. And so basically you've got the power plant. You then basically boost it up to perhaps 330,000 volts. So there's high voltage. And you travel a sort of long distance. And then basically then you start stepping down into your substations. Multiple substations perhaps, before it gets to your home. And the point is, because this is long distance, then the resistance of the wire is basically not negligible. And because P equals I squared R, for a non-negligible resistance, we really want to bring down the power, the current to minimize the power loss. And since transformers reduce current when we boost up the voltage, that's how we do that section. Okay. We'll briefly just go over the basic concept of induction motors, and then we'll start just going through questions. So induction motors are motors as well. So as with all motors, you need a magnetic field and a current. The key thing you need to understand with the induction motor is that the magnetic field is created. Firstly, it's rotating. And it is created by having 3 sets of opposing poles connected to AC, out of phase. So the idea with that, of course, is that by turning them on and off at different points in time, it's going to be difficult to draw quickly, but basically you've got 3 basically you'll have set 1, let's do that in green. You've got set 2, let's do that in blue. You've got set 3, let's do that in red. And basically you turn them on and off at different times. And because you turn them on and off at different times, you're just going to get, so you'll get a rotating magnetic field. So you can imagine if only red was on, it would go in this direction, right? If only green was on, it would go in this direction. If only blue was on, it would go in this direction. Now, it's more complicated than what I'm saying, but simplistically, if you think of it as, for now, just for your purposes, you can think of it as just turn on red and the others are off, okay? And then just turn on green only and the others are off, and just turn on blue only and the others are off. Then you can kind of create this sort of idea of rotating magnetic field. Of course, the reality is that they're out of phase and they're all on at various times, and the sum of those things create a rotating magnetic field, but that will be difficult to draw out without some animation. But as long as you understand the key concept there, that's fine. And how do they create a magnetic field? Well, it's your trusty sort of AC, or connected to sort of each set. So each set will have like wires connected to both, and that will create that. Now, your current is then in your rotor. So you'll note the key thing that makes an induction motor different to your other motors is that this rotor does not have any wires created, linked to it. So your current is in the rotor, and this is an induced current. There is no wires connected to the rotor. The fact of the matter is, because of the rotating magnetic field, this rotor experiences a changing magnetic field. Therefore, it experiences changing flux, and thus the rotor gets current induced inside it, and it is a squirrel cage. And since that squirrel cage gets current flowing inside it, that current will still be in a magnetic field, which then, through the motor effect, then experiences a torque. Now, we can go in detail about how a magnetic field, creates a force on an induced current and so forth. But for the purpose of lots of multiple choice questions and things like that, like you can talk about slip and so forth and so forth. But for the purpose of multiple choice, just remember, basically, the rotor will experience a force that follows the direction of the magnetic field. So in other words, if I'm rotating the magnetic field clockwise, then the rotor will spin clockwise. Without getting into all the details of each and every rule and applying them, just understand for multiple choice purposes, often you're given a question where they're saying, if I do this, what's going to happen to the rotor? So if the magnetic field is rotating clockwise, then the rotor will also follow by rotating clockwise. And of course, anti-clockwise as well. Okay, so that should cover basically all the key theory. Let's get a start now on going to questions, which you should all have a copy of at this point, so you could all open it up.